They've done it. Scientists have entangled atoms in not just one, but multiple ways at the same time, using nothing but beams of laser light. This isn't science fiction. It's the dawn of a new quantum era, where light becomes a sculptor and atoms perform in orchestrated harmony. Quantum entanglement has long been one of the strangest and most powerful phenomena in physics. Two particles, no matter how far apart, linked in a way that measuring one instantly affects the other. It defies our classical understanding of space and time and has been described by Einstein himself as spooky action at a distance. Now, researchers at the California Institute of Technology have taken this bizarre phenomenon even further. They've managed to entangle atoms not just in one property, like spin or energy, but in several aspects simultaneously. It's called hyper-entanglement, and it could redefine the building blocks of quantum information. If we can entangle more dimensions within a single system, we unlock access to a higher bandwidth of the quantum world, one that could radically boost our ability to solve problems too complex for even the most advanced classical computers. The consequences are not just technological, they're philosophical, challenging how we understand individuality and separability in the universe. This breakthrough was published on May 30th, 2025 in the journal Science. The pioneering team behind the discovery was led by Professor Manuel Endres and postdoctoral researcher Adam Shaw, part of Caltech's Institute for Quantum Information and Matter. Their work bridges atomic physics, quantum optics, and the mathematical backbone of quantum field theory. The team focused on neutral alkaline earth atoms, known for their excellent coherence times and ease of laser manipulation. Specifically, atoms like strontium offer narrow transitions ideal for precision control, and this makes them perfect candidates for experiments involving delicate entangled states. To control these atoms, the researchers turned to optical tweezers, tools that use highly focused beams of light to trap individual atoms in a vacuum. Imagine holding a dust particle steady in mid-air using nothing but a perfectly tuned laser pointer. At this scale, even slight temperature fluctuations could destroy the experiment. So, they cooled the atoms to a fraction of a microkelvin, close to absolute zero, freezing their motion, not in the classical sense, but into quantized energy levels governed by the Schrödinger equation. This careful preparation allowed them to treat atomic motion not as noise, but as a resource. Rather than fighting against it, they decided to entangle it. Even the tiniest vibrational quanta became usable channels for quantum information. It's a bit like discovering that the background hum of an orchestra can be turned into an instrument of its own, if only you learn how to read the score. In most quantum systems, motion is a problem. It's unpredictable, messy, and difficult to measure. But this team asked a radical question. Could motion itself become part of the quantum story? Their answer was yes, and they proved it experimentally. They used laser pulses to drive the atoms into well-defined oscillations, choreographing them into a superposition of vibrational states. Think of it like tuning a violin string to vibrate at two notes at once. Each atom now held a melody of motion. These atoms were then entangled with one another through careful timing and phase alignment. The motion of one atom became intrinsically tied to the motion of its partner. But the twist came when they added another layer. The atom's internal electronic states, their configuration of electrons, were also entangled. This dual entanglement in both motion and internal energy created a hyper-entangled system. Such states are extremely rare and notoriously difficult to achieve. The result? A single atom now carried more than one quantum bit of information. It could be thought of as two qubits fused into one particle, or even a building block of a more complex, multidimensional quantum unit. This phenomenon opens the door to higher dimensional entanglement, where each atom becomes a carrier of rich, layered quantum data. And because each dimension operates independently, the system gains in both flexibility and resilience. Professor Endres described it eloquently. We knew how to control the electrons within an atom, and we now learned how to control the external motion of the atom as a whole. It's not just tuning an instrument, it's turning every vibrating part of that instrument into a note in its own quantum composition. And crucially, this entanglement wasn't theoretical, it was observed in the lab, repeatedly and reproducibly. By combining external motional control with internal quantum logic, the team brought quantum systems closer to something resembling orchestral coordination, each atom playing not one but several roles at once. The possibilities from here are staggering. Hyper-entangled atoms may form the next foundation for quantum error correction, the Achilles heel of modern quantum computing. Instead of redundantly encoding data across dozens of fragile qubits, hyper-entangled particles may allow for fewer resources while offering more fault tolerance. For quantum simulations used to model chemical reactions, new materials, or the behavior of exotic particles, this means increased accuracy and reduced computational overhead. And in quantum sensing, hyper-entangled motion states could be used to detect infinitesimally small shifts in gravity or electric fields. Some researchers even suggest they could act as detectors for dark energy fluctuations, if such phenomena exist. Quantum networks may also benefit dramatically. A hyper-entangled qubit could carry multiple channels of information, each encoded in a different degree of freedom, spin, motion, energy, or more. It's like streaming 4 high-definition videos over a single fiber optic line, simultaneously and without interference. And as the world moves toward quantum encrypted communication, these particles may offer the highest density, most secure transfer methods ever devised. There's also a theoretical angle here. If entanglement is the foundation of space-time, as some physicists propose, then hyper-entanglement might help test those ideas experimentally. By manipulating more degrees of freedom, researchers might learn how entanglement itself shapes the geometry of reality. This study shows that by mastering nature's subtlest features, we're not just pushing forward our technology, we're reimagining the nature of information itself. From entangling motion to harnessing dual quantum layers, this isn't just a technical triumph, it's a conceptual one. We're learning to listen to atoms as instruments, using lasers as bowstrings, and drawing music from the very structure of reality. Caltech's work opens new roads toward the quantum computers and sensors of tomorrow. It suggests that the universe may be more computationally expressive than we ever believed, holding hidden information not just in what things are, but in how they move. As we step deeper into the quantum era, one question hums in the background. How many layers of reality remain entangled, waiting for us to tune in? Subscribe to follow that signal, because here we're decoding the frontier, one breakthrough at a time.